the 12th episode of Math and Beyond, Analysis podcast. Today, we are going to talk with Nicola Branchini from Ravenna, my hometown. He's a PhD student in statistics at the University of Edinburgh. And today we are going to talk about probabilistic machine learning. And so I will see you shortly. I'm going to send him the invite. And I will see you shortly. Hi, Nicola. Hi.
Hello.
Hi, how are you?
I'm good. Let me know if there is too much noise background and I'll do something.
No, it's okay. It's okay. I hear you clearly, yeah? Okay. Where are you?
Where am I? I'm in the Edinburgh University Library.
Okay.
Because my university is weird and doesn't allow me to go to the office on Sundays. So I have to go to the library, like undergraduate students.
Like every other mortal person. Okay.
Yeah, exactly.
Okay, so basically I gave a small introduction about the topic of discussion of today and about you. I said you did your bachelor degree at the University of Warwick, right?
Yes, Warwick.
And you did... Sorry?
Yeah, at Warwick.
Okay, at Warwick, and you did your master in artificial intelligence and computer science in Edinburgh, where you are now. And you are now pursuing PhD studies in statistics. And you are doing research in which it can be found in your website in importance sampling and quasi Monte Carlo method, which we will then cover later. So I said also that today we are going to cover firstly probabilistic machine learning, and then later we are going to dive onto your research area. But I would like to start asking you, I think we can jump into it, and I would like starting by asking, let's say, why do we add probabilistic to the word machine learning? Machine learning is already a cool and fancy stuff these days. Why do we need to add probabilistic? What is the difference between probabilistic machine learning and traditional machine learning then?
Yeah, so this is a good question, and stop me if I start talking for too long, because there's many things that could be said to answer this question. So I think that basically, first of all, it's a term that has been used to denote a specific lines of work and lines of research within the umbrella of machine learning, but it shouldn't be taken too literally, in the sense that even when you introduce machine learning in any course, you have to introduce some concepts related to probability distributions, like mean or population mean and so on. So specifically in this context, probabilistic has meant historically the attempt to merge ideas from Bayesian statistics into the context of problems that are more traditionally tackled by machine learning. So it's kind of like, the merging of these two fields. I would like to be maybe much more knowledgeable about history, but I would say that, don't quote me, I think that these things, kind of like, I don't know, at least the most popular works in this area that I know started somehow in the 80s, let's say. And some of the most prominent figures in the machine learning community, the wider one, not necessarily called probabilistic machine learning, have done a lot of work in probabilistic, what you can call probabilistic machine learning. For example, Geoffrey Hinton is very well known in the machine learning community. For neural networks, he has done a lot of work on probabilistic machine learning, which is, again, it's about using Bayesian statistics ideas in the context of machine learning. So machine learning is about learning from data, statistics is also in a sense learning from data, just in but usually different problems with a different approach and different goals. But the common ingredient is data somehow. And Bayesian statistics is about putting some kind of incorporating information, knowledge that you have into probability distributions and treating everything that you don't know somehow with a probability distribution. Literally everything, as much as you can. And the application to these ideas to machine learning has been done primarily for the aim to get uncertainty quantification, which is possible without using these kind of ideas. There are many ways to get uncertainty quantification in machine learning models, but this is using the approach from Bayesian statistics is one of them.
Okay. When you say incorporating information the Bayesian way, what do you mean? Let's say, what do you mean incorporating information? Let's say according to Bayes rule, because I know that when reading for getting some reading some stuff. So prior to this conversation, I saw a very common term, prior and posterior distribution. Why do these two terms comes into play? What's their role? Why is it different, a Bayesian approach to statistics compared to a different frequentist approach to statistics?
Yeah, so I should start saying that this topic, if you want to go quite deep, it has many subtleties, and I'm definitely not like by any means a world expert. I mean, I'm not even a UK expert, let's say, let alone world.
Ravenna expert. Okay, we can say this.
Yeah, maybe. So I might say things that are a bit, like, I don't know, superficial or like, but to the high level, the main difference is that in a Bayesian approach, you try as much as possible to put probability distributions on things that so that you model what you don't know with some probability distribution. So in classical statistics, usually you are interested in inferring the parameters of some model. There are some true parameter or some true quantity that you don't know, like, I don't know, the average IQ in the population, or the reproduction rate of COVID in this area, and so on. And so you treat there is this quantity or multiple quantities that I don't know, and I'm going to try to do some stuff to find out, to provide an estimate of this thing that I don't know. In Bayesian statistics, you say, okay, I don't know it, but basically before I see any data, or before the analysis, let's say, I specify kind of a probability distribution on everything that I don't know, that somehow models my degree of belief in what are the possible values if this quantity is a number or multiple numbers. What are the range of values and their plausibility that I believe subjectively as an analyst. And then the data is used to update this distribution. As I said, there are many subtleties in the sense that there are also attempts that, I said this subjective kind of distribution. There is objective, Bayesian statistics and objective priors. There are many things that people have done and many variations of Bayesian statistics. And also the most fundamental difference is also the interpretation of probability within Bayesian statistics and frequencies. So in Bayesian statistics, essentially, for example, many people have argued to use a different symbol instead of, probability or P of A given B, for if it's Bayesian or with frequency interpretation. Of course, in mathematical sense, the interpretation doesn't matter. The mathematical definition is not ambiguous of probability, but the interpretation is there are many interpretations, and in the Bayesian context, the probability means a degree of belief, whereas in the frequencies context, it means somehow there has to be an underlying thought experiment that can be repeated multiple times, and the probability signifies the frequency in relation to this real or thought experiment. So one of the first motivations for Bayesian statistics is that it's a bit awkward to give a probability to events that are one-off, like what's the probability that humanity gets extinct? And if you use the frequency definition, it's a bit weird to discuss this, how to assign a probability to this statement, because it cannot be repeated by definition. So that's why people have been interested in alternative definitions like the Bayesian one, where probability means a degree of belief. And also there's reasons like these Dutch book theorems that kind of like if you start specifying some axioms about an agent that reasons logically under uncertainty and has to assign a numerical value to the degree of belief in certain propositions, then you can show that the only kind of like possible way to do this in a consistent way, so without making self-contradictory statements, is if these numbers sum to 1 and are non-negative, so with probability. So this is also something that people like as well, although again there are subtleties, because maybe sometimes you can argue that in this axiomatic framework where these theorems have been derived are not necessarily always appropriate for reality and so on. Yeah.
Okay. And I would say back into our topics of probabilistic machine learning. But wait, before that, I want to ask you. So basically, what the bias approach says is, okay, we do make a sort of a guess, and then we do observe data, and based on this data, we do update our guess onto some other distribution, taking into account the behavior of the data observed. Is that right?
Yeah, that's the intuitive explanation.
Okay. So now back onto probabilistic machine learning. Why do we? So basically, let's say said very brutally, I think difference between probabilistic machine learning and traditional machine learning, let's say, lies in the handling of uncertainties of our machine learning system. But why do we need why is uncertainty important in machine learning, and why do we want to keep account of it?
Yeah, so uncertainty, I would argue, is always important, regardless of whether you take kind of like a Bayesian type of uncertainty. And uncertainty is important because the models are used to make decisions in the real world, and usually you would like to know kind of like your model spits out some numbers, and you would like to know, that those numbers are not always 100% accurate for sure. And especially in critical situations, let's say this decision that this number will lead to. So I don't know whether we should based on this an estimate of the R number during the COVID pandemic. Should we close the schools or not? If if your model, the computer that spits out 3, then okay, it's 3, but like maybe it could be between 3 and 5 is more reasonable, or maybe it could be between 3 and 10. So a very crude measure of uncertainty is like an interval, right? But the ambition of Bayesian statistics is to get a distribution which is a qualitatively richer object than just an interval. And yeah, so it matters because of decision making, basically, especially when the decision has some real impact. But almost always it has. It's just a matter of how important the decision is. Sometimes it means that you maybe just profit a bit less if your decision is ill informed, and sometimes it means that lives get lost. So whenever you have to make decisions, you need some level of quantification of uncertainty that is reliable.
Okay, how do we take account of uncertainty? How do we handle uncertainty in probabilistic models?
Yeah, so in probabilistic models, or which are models used in probabilistic machine learning, you have with the Bayesian approach of specifying these posterior distributions. The challenge is, first of all, in having models that kind of represent reality in an accurate way, and perhaps that's the most challenging thing. But let's say that that's been done. So you specified a model that kind of like well represents reality, and you have a lot of data. Then there is another challenge that is what people have been focusing in research for many years, which is actually computing, the uncertainty estimate once the model has been built, which is seems kind of like easy in the sense if you're not too familiar with the area. Okay, you have the model, now you just have to do things with it. So ask the model what's the probability that this happens, if that happens, and so on. But usually this involves some kind of computationally very intense task, especially in the context of machine learning models with big data sets and so on. And so computing uncertainty involves essentially computing very computationally intensive expectations, or like integrals at the most basic level. Everything in probability is some kind of integral. If we are dealing with data that is like real valued, or there are some numbers that even if they are discrete, often you have big sums, let's say, and the whole of Bayesian statistics these days are even called Bayesian computation as a field, because it's focused on how to do this efficiently.
Okay. And what do we, let's say, where do we find in some task? Let's put it this way: what are some common problems where the need of the probabilistic approach arises?
Yeah. So one of the most popular ones, at least at the research level these days, is when you have a very expensive you're doing some kind of very expensive experiment, either in the real world or just on the computer, and this experiment, let's say that you're I don't know, let's say that you are at CERN and you have your particle accelerators and so on. Yeah, the experiments are very expensive and so on, and there are some parameters that you have to tune that you have some idea of what they are doing, but you have to try several values, several combinations, and see what happens. And and you have some measure of whether the output of the experiment is good or bad. Usually you have multiple ones, but just to simplify. And so there is a problem that very general problem of can be formalized as kind of like optimizing an unknown function. Unknown in the sense that you can ask it, okay, I give you some input values and I get some output back, but I have no idea how this function looks like, right? But still, I want to find the settings of its inputs of the knobs that kind of like maximize it or minimize it. One of the two, it doesn't matter. And this black box kind of like function optimization is called more formally global optimization. It's a global optimization problem. And because you assume that even asking kind of like one question to the function, so like getting one evaluation of this function at some input values is very expensive. You'd like to minimize or maximize this function with as few evaluations as possible. And in this context, it's very natural to try to model the function in a probabilistic way. So having a belief of what the function looks like that is updated as you get more data, more evaluations of the function, essentially, that tells you, okay, I believe now that at the start, I had no idea how my function looked like. So maybe it looked like I had a belief that is like flat functions, constants. And then maybe I observe some points. And now I think, okay, my function goes through these points, and you can incorporate your beliefs in and formalize them to a probability distribution over these functions, this underlying function that you're trying to minimize, and this can help you in deciding, what kind of like experiment to run, such that you get a better output. And these techniques are called Bayesian optimization, and they are very, very popular at the moment, especially in scientific fields like theoretical chemistry, or essentially it should be anywhere where kind of like computationally intensive experiments are run, and there is and it's possible somehow to model the underlying system in a probabilistic way to specify some kind of knowledge that you have about the system in a probabilistic way. And then, Bayesian optimization is one very famous example. And then, for example, another one is in the context of, at least as far as I know, tracking of drones or any kind of robots that move in the physical world, and has some sensors and has to infer kind of like where it is and where other things are, because the sensors are imperfect, right? It cannot have like exact estimates and say, okay, I am here and this thing is here and this other thing is exactly here. It has to have some probability distributions and continually update them. So probabilistic machine learning or probabilistic reasoning is used a lot in historically in even military context, with like robots that move around in the physical space. And,
Okay. Can you expand quite briefly on Bayesian optimization, because I believe we will need it a bit later.
Yeah. So as I said, the key idea of Bayesian optimization is black box optimization of a function. And black box means, for example, that you cannot do things like in traditional machine learning, where you have a loss function and you have some data and you do gradient descent, because the idea is that you don't have that much knowledge of this function that you can get a gradient and then optimize. All you have about this function is input output, kind of like you throw it some valid inputs, it tells you what the output is, and that's all you have. And then you also have some kind of like prior knowledge, which you incorporate through your probability distribution over functions. And the tool used to do this is usually Gaussian processes, which is mathematically, again, it has a very, it's not even, I don't believe it has been developed for this particular application originally. Gaussian process, just a stochastic process, such that the finite dimensional distribution of any kind of like, subset of the variables is jointly Gaussian. And it just turns out to be a very useful tool to specify distributions over functions. It has many favorable computational properties and interpretability properties. So it's just convenient. And maybe if someone is not necessarily familiar with this area, it does not mean that you assume that kind of like the underlying observations are somehow Gaussian in the sense that you would naively think. Right? You're not making extremely strong assumptions in this sense. You are making some strong assumptions when you use these, which are almost always are the only thing you can use anyway. Gaussian process to model a belief over function. You're making some kind of smoothness assumptions that are depending on certain concrete choices that you make, because these Gaussian processes have some parameters. Often it is the case that you make very strong assumptions that don't hold in reality. But because they are so convenient, still people try to kind of like fix them instead of using something else entirely because they're so convenient to use. Tell me if you want me to elaborate on specific aspects more of Bayesian optimization, maybe.
Okay, maybe we can dig into it later, as we will cover a very similar topic related to your research. But now, just to keep on moving with probabilistic approaches in machine learning, what are some other and what are some challenges? Let's say when developing and dealing with fully probabilistic approaches to machine learning, and how can you address them?
Yeah, so the classic response to this is again kind of like computational tractability. So whenever you try to model what you don't know with probability distributions, you introduce some kind of additional integrals that you have to compute, essentially, or estimation of distributions that often are specified. These distributions are specified for a lot of parameters, and they are very complicated. You don't know how they look like. You cannot write. Even if you can write down sort of like an equation that tells you what the distribution is, it does not mean that you know how to compute its, let's say, mean, or how to compute certain quantities related to it, like, essentially are always come in the form of expectations. It does not know it does not mean you know the shape of this distribution. And if it's in high dimension, it's even kind of like awkward to talk about certain things that are intuitive in low dimensions, like like the shape, because the shapes in high dimensions do weird things. And so it becomes very computationally challenging to compute the things you would like to compute. And also, I would add something to the usual response, which is not only it's computationally challenging, but really, I would say what's even a bigger problem is that even if you have a lot of computation, you often have you don't have a good idea of how to be sure that your final answer is somehow how far from the truth it is, or how accurate. Or for example, in many techniques used in approximate Bayesian inference, don't really have good good metrics, like because you know that let's say, okay, maybe in the limit to infinity you get the right answer, but in the limit, as we often say in this research area, we are all dead. So sometimes you are able to have some kind of under very strong assumptions, some guarantees that are not at infinity. That is what really you'd like to have. But the mathematics is extremely, there's kind of like this jump, like it's a step function that giving guarantees at infinity is quite okay, and then becomes extremely impossible, close to impossible to give any kind of guarantee for any sample size that is not infinity. And so people go with heuristics and praying that the thing is working, basically. And yeah, this is it's a extremely big of a problem that I would say is not even that well advertised within the field, in the sense that basically most people have kind of given up, or like, okay, it's good enough, but they think it's good enough that the metrics that we have now to kind of like evaluate how our algorithms kind of like if they are doing well or doing bad, like how far from the truth they are. And I think that it's kind of wishful thinking, in the sense that they are not good enough, and we just kind of like, the problem is too hard, so we have kind of like given up. And yeah, but yeah, I think when this is also an interesting problem, and perhaps even more of a problem nowadays, where there is a lot of computational power, compared to like 20 years ago, where some things in this space you would say, okay, we cannot do this because there is no one can do it. Like, no one has a computer that could do this. Now, maybe you say, okay, actually, I don't know, if I'm at Google, I could, and I convinced enough people that this is important, I could get the computational power required to do this, and be quite sure of my answer. But then still you need, because again, infinity does not exist. You still need kind of like, unless the problem is very easy, you need good ways to evaluate your output, like mathematically kind of like grounded, or statistically grounded metrics. And yeah, those are also still missing from this field.
Okay. What are some, let's say, cutting edge, what is the research frontier with regards to this topic? Or let's say brutally, what are researchers spending most time now at the moment?
Yeah, so I just been to a conference, the main, I would say, in my knowledge at least, the main conference that is specific to Bayesian computation, like, last month. So maybe I can feel kind of like what was were the most popular topics there, which were people are very interested in the one I think I mentioned before, which is specifying your model such that it represents reality well, even before you do any computations with it. So this go under the umbrella of model misspecification. And in this field, we all know it's a cliche that to say that basically all models are wrong in statistics. But now people are getting serious about it, or trying at least to get serious about it, and trying to handle like what to do if you assume that the data has this distribution, and that is, I don't know, unimodal, and instead it was bimodal. Is the underlying methods that you use to compute things, are they robust to this kind of misspecifications of the underlying problem? This is a very big topic at the moment, and Another big topic is to perform Bayesian inference in the context where if you cannot compute a likelihood in a simple way. So as we said before, Bayesian inference is about updating distributions from a prior to a posterior, and you need also a likelihood to do this, which incorporates kind of like the information from data. And in many cases where you want to do Bayesian inference, the data generating mechanism is very complicated to model. You cannot just write down some equations and kind of like get a likelihood that for any parameter value gives you a number very easily. It's maybe it's a neural network, maybe it's a simulation black box model. And so in this context where you cannot compute a likelihood, or it's very computationally expensive to compute, so you compute a fake kind of like representation of it, or a surrogate likelihood, it becomes harder to do proper Bayesian inference because one of the ingredients is missing or it's imperfect. So people are really interested in this likelihood-free inference. It's called the field. It's a very big topic at the moment. And yeah, I'm trying to think what are other big topics at the moment.
What do you think is that has been done the most? Let's say the most progress, the most advancement in the latest year. Which sub area within this field has, let's say, displayed has had the major development?
It's a good question. Well, I would say at the methodological level, it's a field that does not progress, nearly as fast as popular machine learning fields like the neural network based fields or language models at the moment. So in 1 year, I would say usually not much happens, not too much happens, but I think that this particular field of misspecification has had some significant uptake in the last, not year, but maybe like more like 6, 7, since the publication of a few kind of like very popular papers now. And so if I had to pick something, that's what I would pick.
Okay, I understand. Now I would like to start delving more onto your research area. And so I said before that your research area is about importance sampling and quasi Monte Carlo methods, which are cool names. Congrats, Nick, you study very fancy stuff. But can you elaborate more simply? What are these topics?
Yeah, so it makes sense to introduce kind of the idea of Monte Carlo and Monte Carlo method, which is at the very higher level. It's about computing kind of like typical integrals or expectations, which are kind of the same thing, more or less. So you have an underlying quantity, which is real valued, or is not necessarily an integral over in one dimension. It should be a multi-dimensional integral that you don't know how to compute, and you want to approximate value. Maybe because it represents, for example, the probability of some event in the context of your probabilistic model. That's the most typical application, right? So you have a model of this system, and I want to compute the probability that it failed, for example, in this particular way. And this probability is an integral because that's how questions come in probabilistic models. They are integrals. And to compute it, you need a generic tool that can do it for almost any kind of integral. And the Monte Carlo method does that. So it's it's a method to compute integrals in a very generic way. Also, using the underlying function that is inside the integral as kind of like similar to black box in the way I said before. So kind of like input output type without making very little assumptions. And it basically intuitively what it does is kind of like it goes into the space of possible values that this function can take. Well, it's more like the space of possible inputs. It takes points at random and it plugs them through the underlying function, which is the thing inside the integral. And then it takes some kind of average or arithmetic average. It's very general, it's very simple to do in practice, to code, extremely simple to code, at least the basic version. And it has some very easy theoretical properties to analyze. And it gives you some level of uncertainty quantification because of the randomness that you choose these points at random. And then one could talk about what kind of uncertainty quantification it is, because in this case, it would be a frequentist kind of uncertainty quantification, not very Bayesian. But yeah, it's been ubiquitous in kind of any field that requires some computation with the expectations or integrals because of its simplicity and broad applicability, I would say. And it can be described, the way I also describe it usually is as a randomized algorithm for integration. Background noise. And specifically my research for an important sampling is about making kind of Monte Carlo, the basic Monte Carlo method, more efficient in the sense of these random kind of like values, random samples that you obtain, you want to use as few as possible, because sometimes they represent some kind of expensive process to get them. And yeah, important something is basically the main idea behind efficient Monte Carlo.
And how do you do that? How do you do efficient Monte Carlo? How do you, let's say, make the process more efficient? Indeed.
Yes. So thinking about an integral that is specifically a typical kind of expectation. So the mean of a distribution. The mean of a distribution, the definition of expectation is kind of like, the integral of x times the distribution of the density of x, and then integrated over the whole kind of support of the distribution. And the basic intuition is that if you sample from the distribution itself, which is the basic Monte Carlo method, so you get points at random according to the distribution that defines, or the density that defines the expectation. And then you average them. You do kind of like a simple average, like 1 over n times the sum of the points evaluated, in this case, x. So just the average of the points to compute the mean of this distribution. The important sampling idea is about that if you sample from the distribution itself, you are sampling where the density is large by definition, essentially, of the distribution, because if you're more likely to get points where there is probability mass, which, okay, unless we are in like very high dimensions, and let's ignore that case, like it's where the density is large. So by definition, you are sampling points where P of X is large. But this means, for example, that this integral is the product of X times P of X. So you are sampling points where P of X is large, but maybe you are ignoring the other kind of like term inside the integral, which is the X itself. And really, if you want to be as efficient as possible, you should sample points where both of the terms are large at the same time to get the most kind of like out of your points, sample points. And this is the main idea, main intuition behind important sampling, I would say. So you try to sample from something that is not actually the density that defines the expectation, and try to sample points in areas where the entire kind of like thing inside the integral is large, which in this case is just the product of two things. And the way you do this is you sample from a different distribution that is not say the P of X, as I called it. And because you sample from something else entirely, you have to for mathematical reasons, kind of like to get a valid estimate out of what you're going to compute, you have to reweight the points. So before you just did an average that is like 1/n sum, and now you have to have each point has sort of a weight, and the weight is basically going to be some kind the ratio of the original distribution and the distribution you're using, evaluated kind of like in that point, or density more like the distribution of yourself. And the intuition is that kind of like points that are receive a high weight. They receive a high weight because they have large probability under the true kind of like distribution that defines the expectation, and but they have maybe like lower probability under your own kind of like thing that you sampled from, so they should be counted more than other points. So they are underrepresented in the sample because they should be represented more. You would like to have more of those points because they have large probability under the true kind of like distribution.
Okay,
so
can you repeat how is the ratio defined? Which PDF over which PDF?
Yeah, so let's say that you have your X is the variable, and then P of X is the true density. Then you sample from some arbitrary distribution, which is Q of X to the P, and then your weight in this case would be P divided by Q.
Okay.
And this is a bit of a lie in the sense that the whole point that I said at the beginning is that the thing you sample from should take into account not only the P of X, but also the X. You want to get points where the product of P of X times X is large. So really the true, like the weight that matters is X times P of X divided by Q. But people, for simplicity, usually look at the distribution only and forget what the other part. But really, when you choose your Q, you want to select it such that it says you get points that are very likely when both terms are large, and when that happens, you tend to get weight defined as kind of like either P divided by Q or X times P divided by Q. In either way, you get weights that are not very variable. They are all almost the same value. So let's say like they are all a constant, and ideally, you get an estimate of the true value, which is almost always like close to the true one. And because it's a random estimate, right? So that's why I say almost always, because there's going to be variability, but you want to minimize this variability, and you want to have properties that are either of the importance sampling estimate or the basic Monte Carlo, which is a special case when you choose the Q is equal to the P. So and you wanted to have kind of like the right value on average, which means unbiasedness, right? And you want to have small variability as well. So the variability of your estimate should be as low as possible. This is the basic way to evaluate the goodness of your answer. And what I described is kind of like the basic importance sampling idea and principle, to kind of assign a weight to some point such that you reduce the overall variance, really, because the basic estimators, Monte Carlo and simple importance sampling, are both unbiased. So all you have to think about is the variance. And then from there are many things you can do to kind of like do things as efficiently as possible. For example, have this thing that you're sampling from, it could be something that has a parameter that is tunable. So, and then you change it over time such that the thing you are sampling from is as good as possible. By good, meaning that it gives kind of like final estimates, which are low variance. So you iteratively change it. You sample some points, then you change the parameters. So the way that you are sampling, you change it, and you iterate, and so on. And this is called adaptive importance sampling. And for example, I would argue that, and I don't think this is I don't think it's controversial. I think it's just a bit forgotten these days, but this idea has been used without calling it this, really, in many machine learning contexts, where the term variational inference is more popular. It's just another term to denote kind of like a method to approximate probabilities, expectations, and so on, just in the context of machine learning. And there, it has been very popular to kind of like have approximate an underlying integral with kind of like sampling from something, whatever you want, that has some parameters. Then you compute some measure of performance. In this case, let's say the variability of the weight or the variability of the estimator. And then you change the parameters of the thing you are sampling from, the Q, I called it before, and you iterate and so on, so that it improves performance over time.
Okay. Did you use now? I want to let's say go a bit over the paper you recently wrote, which you published and you presented at the conference AI Stat, right? And it is called causal entropy optimization. First thing, did you use this concept of importance sampling? And second thing, before, that's why I said yes, let's dig a bit into Bayesian optimization, because let's say that we can relate causal entropy optimization and causal Bayesian optimization. So what's let's say, what's the matter with the causal entropy optimization?
By the way, just it's a funny kind of like thing that is even a joke in the field, because you said causal many times, and it's causal.
Causa.
But no, but it's fine. Don't worry. It's just because casual, means sometimes as well, like kind of like, yeah, things are done at random, like, and it's usually like you say it even as a joke instead of causal. But yeah. So okay, I can tell you about the paper. And the first question was if we use importance sampling inside the paper, which is no, in the sense that we use Monte Carlo at some moment, because whenever you're doing some approximate Bayesian inference, at some point you're going to use some Monte Carlo for sure, almost for sure. So there are, because in the many things that we do inside this project, kind of like at some moment you have to compute some integral or some expectation, and there we use simple Monte Carlo. And the reason I did not use importance sampling I guess it was for speed, because I was trying to get things done as fast as possible and get something simple. And also because it can be challenging in the things I would have to have used it for would have required some challenging implementation, because one thing that important sampling assumes that I have not said before, which is the key to why you can make Monte Carlo more efficient. You never get anything for free in life. This is a good general principle in research as well. You can get more efficiency. There is kind of like, because you're using slightly more assumptions somewhere, which is a feature of any method. And it's because in important sampling, you assume that you can evaluate pointwise for example, the P of X that I said before. So if you use simple Monte Carlo to approximate the mean of something, so integral of X times P of X, you just sample from the density and you average the points. So all you need to evaluate as a number is like the sample values, and you average them. But now if you have the weight, it means that you can pointwise evaluate the density P and also the thing you use to sample the Q. So basically you need to evaluate these weights, and this is not always possible to do. And I think that in the Monte Carlo application that I used in the paper at the moment, I don't think it would have been easy to do this. So I use simple Monte Carlo for that reason. Okay. About the paper more in general, yeah, so really it makes sense more. It's a paper that is based on previous work by my co-author Virginia, and the whole kind of like line of research is based on incorporating causal information into Bayesian optimization. So when the function you're trying to optimize, as I said before, it's a so-called causal effect. So which formally means it's just the mean of some distribution, and this distribution happens to be so-called interventional distribution. So what that means is that it's the distribution that of a probabilistic system that under some intervention or under some change. So there are intuitions behind this. So let's imagine that, probabilistic system is just a set of kind of like variables, a set of quantities that have some distribution because there is randomness. So they have a joint distribution, and you can represent this in code. So how to generate random things in code? You start by generating some noise, a random noise. Then you have some deterministic functions that take this noise and input and transform it. And then maybe add additional noise, then transform it again, and so on. So you have some lines of code, right? The first line generates some random noise. The second line takes this noise as input and then produces, maybe it's a sine function. It's some complicated function. It doesn't matter. Produces an output that is going to have some distribution, which is related to the one of the noise. Maybe a very simple one, but now it's more complicated because you passed it through something. Then this thing itself is passed through something else, to another deterministic function that has some other added independent noise, gets you another line of code, and so on. So this is a process for generating data that has some complicated distribution, the way you do it in code. And the distribution of all these variables is called the joint distribution. Now, in causality, you are interested in the distribution, not only this distribution, but also the distribution that you get if you take some of these, any of these variables, and you delete the line of code that assigns its value to it, and you replace it with if the variable was called z equals 5, and you leave everything else unchanged, right? So what that means is that you fix that variable to a certain value, that variable is not random anymore, but everything else still is, because that's the only line of code that you changed. So there is a different distribution on the whole system, all of the variables, but it's related to the original one, and it represents the probabilistic behavior of the system, of the original system, under a particular intervention, so under a particular change of in the system that you did. And this is of interest, not only in this kind of, now I described a simulation kind of way to simulate this, but for example, the motivating kind of like applications are the idea of causality is in whenever you want to do something, an experiment in the real world. So let's set the dosage of a certain drug and then to have some value such that you minimize some reaction, like bad reaction in the patients, right? And there, causality is important because you really want to ask what happens if I do this, or like, in the code sense, like there is the process that generates the data is the reaction of patients to this drug. But as kind of like when you learn causality, you learn that kind of like seeing is different than doing. Is kind of one of the mantra, let's say, or which is the same as saying, correlation is not causation, and to infer to make inference about things that you would do, you need to do an experiment. So you need to or you need to, do the actual intervention and then see what happens and get the results of this intervention distribution. So in this context of causality, which I just kind of like briefly summarized, we can do Bayesian optimization. And the main idea in this research line is that because you know something, before I said that this function is very black box, input, output, and so on. In this case, you have additional information that you can incorporate about the function. And this information comes in the form of, for example, a causal graph, which means that you know something about the distribution of these variables, and you know that this one affects that one, that this one affects the other one. So there is a directed graph between the variables, and you can use this information to kind of like have a more accurate representation of the underlying causal effect, or like the underlying function that you're trying to minimize or maximize. This was the main idea behind the first paper, which was by Virginia. And then in this particular one, we tried to still perform Bayesian optimization in this context of causal inference, when the underlying function is a causal effect, but when you have some kind of uncertainty over the causal graph, so you don't have it specified exactly. So, for example, it's kind of a Bayesian way, although the statistics formally are quite hard to do. But so we did this quite empirical paper. So we specify a distribution over graph, and then you use that to take into account that you have kind of uncertainty over the graph. In informally Bayesian approach, right? You have something that you don't know, then if you don't know it, you model it with some distribution and then take expectations over that distribution.
Okay. What were let's say challenges you faced when working on this paper?
Challenges when working on this paper, I would say, as in any paper really, is to think about experiments that make sense, that showcase the idea that you want to portray, to formalize what you are trying to do in as clear way as possible. The main challenges with any kind of like methodological project in statistics or applied statistics, machine learning, and so on, where you're trying to develop certain methodology, the challenges are always, yes, kind of like going from, really formalizing as much as you can with the purpose of clear communication, not with the purpose of, as unfortunately, I mean, it's very common and well known. It's a cliche that people use mathematics sometimes in the same way that in the humanities you use kind of like unnecessarily long and complicated paragraphs or like fancy words to showcase your kind of like your virtue in like being able to do complicated things, like but for no other purpose. Maybe I don't know, I'm not an expert in literature, but maybe in literature it's still fine because or maybe it's just for entertainment. But for in science, it's clearly kind of like bad because it's like obfuscation when the purpose of science is like to communicate like as clearly as you can, to make things complicated. So it's always hard to be precise, but at the same time not introduce unnecessary obfuscation, which usually comes in the form of complicated mathematics, and then to perform good experiments. That's challenging always, because especially in the settings of like this paper where there are many knobs to tune and many things that can go wrong, then that's always a challenge.
Okay, what in general about your research area, so importance sampling and the Monte Carlo methods, do you have do you face similar challenges, or do you also have any other, sort of problem that you, that struggle that you stumble across your research, activity?
Yeah, so the work I'm doing now, it's similar in a way. It's a bit on things that are simpler. What does simpler mean? Well, let's clarify. It means that the settings that I am trying to develop methodology now are have less knobs to tune. They are more controlled, whereas the developer of methodology have more control over, so it's easier to kind of like know what's going on, and to make conclusions that are kind of like accurate. But many of the same challenges remain. For example, on the formalization level of you get an idea and want to formalize it. And also many of the same challenges remain in the form of kind of like developing a technique that has not already been used, or like kind of like checking the related literature. Things get reinvented all the time, and sometimes it's even unavoidable, because maybe the thing you just come up with was done in a paper in 1980 that has 3 citations and no one has seen it before, or it was forgotten. So it's kind of like, sometimes it's unavoidable, but in most cases it's avoidable by doing a good search. And then a challenge in research in this, I would say any methodological research, is always to really, first of all, understand the problem at hand. The incentives in publication is always to kind of like somehow say that what you're doing leads to improvement somewhere, or leads to things being better in some way. But the difficult part usually is to understand really, okay, where can you get benefit by doing something different, why it makes sense, communicating it in a clear way, and so on.
Okay. Yeah, still trying to arrange all the information I with regards to the paper I heard. How was the conference? How was presenting the paper at the conference? Was it your first time?
It was not my first time presenting at a conference, but it was my first time at a big machine learning conference, with AI stats in this case. And yeah, no, it was definitely very nice. And within the machine learning conferences, this is perhaps the big ones. This is perhaps the one that is also most aligned with my research interest, which can fall under the spectrum of probabilistic machine learning. And so it was nice because there's many people doing things that are around my interests, let's say. And it's because of that reason, it's relatively smaller than the very big ones. And so you can talk to most people. And this is one of the best parts of doing science, right? I mean, to meet people in the same community and kind of connect and discuss ideas and meet the people behind the papers, let's say. But then usually you find that, they are kind of like, you have many things in common, and they are also complaining about having to do things that are required to get through reviewers, but they really would like to do something else, and so on. So it's always very nice.
They always complain about there's so many papers being published every year by so many researchers, I guess.
This is a whole discussion, but everyone complains about obviously kind of like too many papers that the incentive to publish more and more, and also that means that there is gets harder and harder to know what to read as well, because there is so much kind of like that goes online all the time. So it's a problem that doesn't have any solution at the moment, and none is in sight for the next 20 years, I would say, for sure.
Okay, hopefully. I was talking about this with I once went to Grappa, which is a physics and astrophysics institute at the University of Amsterdam, and a visiting professor from I don't remember which university, but a university in the States. She was also pretty much discussing this with some postdoc there when she had a public lecture, and then basically she said the exact same thing, but then she said, how can you change this when basically funding and like research opportunities are given on the basis of these kind of metrics. So how productive you are, how much do you publish, and so that's pretty much that's pretty much built around the fact that funding and opportunities to do research are given based on those metrics. But hopefully that may change in some future year, even though not many people do have a practical solution to this. But okay, I think we can wrap it up here. It was very nice, very interesting conversation, and even, let's say, different from the type of conversation that I have had in the past. So equally exciting, and absolutely, I hope I will, maybe in the future, I don't know, when some other paper will be published, you may come by and pass again.
Of course, it was a pleasure.
Okay, so thank you, Nicola, for your time. Thanks for this episode, and thanks everyone for listening along us. And I will see you in the next episode. Bye.